A quick impromptu video here. I was going over the problem I just uploaded the other day, the baseball problem, optimizing the baseball problem, what angle gives the maximum distance. And I was getting a little annoyed at the code because tweaking small things like the number of data points used in the integration and the final time using the integration caused fairly significant deviations in the changes in the optimal angle, and that really shouldn't be. These algorithms are generally pretty good and should give a consistent answer. And it turns out there are some issues with the way SciPy's numerical integration ODE package works. So I just wanted to quickly show what those are and maybe come up with a quick workaround. I'm recording this on January 1st, and I live a couple blocks from where the Rose Parade goes, and it just got out, so there's still tons of traffic, and so if there's any traffic noise during this, I apologize. But anyways, let's get on with it. So here is code essentially taken from the test code I wrote. This is the Python code that has the system of differential equations as a function, has the event detection function, and then has a function called calculate trajectory that takes a time instead of an angle and integrates the system of equations from 0 to that time and returns the points such that the cutoff is, when the cutoff is reached, it returns all the points up to that cutoff. And down here I've taken some data from some simulations and the actual algebraic answer that we got here of 180.66 meters. And the error for these criteria, so we're running this simulation to 5 seconds and we're taking the number of t-eval points to be 100. So when we run this, we get an error basically of like 1 meter. So let's just run this code and see what happens. So you notice here, here's a plot of the data. This never reaches 0. So what's happening here is the system is integrating the equations. It detects an event and stops integrating past that event, whereas I assumed that it had interpolated to get the value at the event time. So if we look here at our actual data, the range is actually 179 meters, so it's like a meter short. And the event time is here. It's 4.6635 seconds. So if we go back to here, here is the equivalent code down in this little window here written in Matlab. So if we go over to Matlab and run this, you notice here it does go all the way to 0. So if we zoom in, well, that's pan. Okay, pan. Where's my zoom? It gives us the point at 0. So that's a known issue with the Python library, apparently, that it does not actually give the proper answer. If you notice here, well, if I calculate the error out to wherever the decimal percentage is shown here, it's essentially 0, and we actually calculate the exact value. It's like 10 to the minus 13 between the real error, the actual value, and the simulated numerical answer. But the event time is the same. So Python does give you the correct event time. So how can we work around this? I'm going to shut down, no, I'll keep MATLAB running for the time being, but I will go to here and I will close the MATLAB code. So what I'm going to do is just simply modify this code to give us a better interpolation, give us a better estimate of the range. So for the time being, I'm just going to actually just get rid of this, get rid of the plotting, just comment these out because I have the numbers written down here. So so we don't really need them all that much. Comment out, comment out, comment out. We're going to need some of the interpolation functions from SciPy, so let's just kind of enter them in here. So we're going to use the interp1d command. This won't be the most efficient of ways to do it, but what I'm going to do is come down here. I am going to get the time of my event. So t, we'll call it t underscore evt, is equal to sol.t events 0, 0, and let's just print that to make sure we're actually getting it. T evt. Let's go here. Okay, that looks good. Let's move on. So we move back here. Let us copy this, paste that down here, and I'm going to call this solution 2, and I'm going to get rid of the events part of this. And then I'm going to grab t is equal to sol.t, x is equal to sol.y, it's the 0th row, all columns, yank and put. Let's get the y values out of here, and this is now equal to the second row in all columns. And let's just make sure we're getting this correctly. So plt.plot x comma y, let's make them dots, plt.show, run. Okay. Oh, this has to be sol 2. We're now looking at solution number 2. And you see now that this one goes below 0, which is just what we want. So we go back here. We don't need this. Oops, what did I do? Delete, delete. We're going to create an interpolation object. Let's call it SP for spline. That's going to be equal to interp 1D. We want t comma x, and then we're going to print SP evaluated t evt. Error. Interp 1. Interp 1D it should be, I believe. There we go. So 180.6647. And what's our actual number? 180.6647. So we're good out to several decimal places. So obviously this is just kind of printing out the numbers kind of in situ. It's still returning the wrong answer. In a future video or future, maybe I'll just update the notebook at a later time and date, but for the time being I'm just going to keep things as is. But I just wanted to get this out quickly because it is a potential issue with code, and it's something you might have to worry about if you use SciPy rather than Matlab for this type of thing. So okay, until next time, see ya.